Hi, my name is Drahos, and my partner Faizan, Malik, and I would like to take the next couple of minutes to present to you the design of our handheld tissue grasping device, capable of measuring tissue mechanical properties in vivo or in a laboratory setting. To start things off, I'd like to discuss the overall background and inspiration for this device. A key phrase that the sponsor of this program, the Army Futures Command, uses to drive their research is that next generation simulators should be more lifelike and not dead-like. Most of these medical simulators that the Army uses today have tissue mechanical properties based on testing of preconditioned tissue in a laboratory setting, and the assumption is made that the tissue mechanical properties of most tissue do not change from in vivo to the tested preconditioned state. While this appears to be a widely accepted assumption, there is a surprising lack of physical evidence from testing tissue samples in vivo to an ex vivo state in a laboratory. This is primarily due to the fact that it is incredibly difficult to test tissue in vivo, thus this is where the handheld tissue grasping device concept was born. This leads to the question of why are other tissue mechanical property testing devices not capable of testing tissue in vivo and in a laboratory setting. The most common tissue property testing device makes use of testing tissue under tensile load, which works great in a lab, but is nearly impossible to do with living tissue. This leaves compression-style tissue testing devices, which often make use of an indenter that presses down on a tissue against a rigid backplate to record tissue compression and applied forces. Again, this works great in a laboratory setting, but it's not feasible in vivo, as there is often not access to a rigid surface to press the tissue against. Now that the shortcomings of alternative tissue mechanical property testing devices were understood, these shortcomings were used to lead the design of our grasper device. The grasper device is shown in the top right figure of this slide, which consists of two 5-kilogram load cells at the grasper jaws to record applied forces to the tissue, and a rotary encoder at the center to record angular position of the grasper jaws, which is used to calculate tissue thickness and overall strain. The signals from both load cells and encoder are recorded via a National Instrument DAC card, which is fed to a computer running a back-end software created using Rust that both saves the data to Excel files, but also provides the user with live readings during testing. The primary design requirement for this grasper was that it needed to be capable of being implemented during in vivo tissue testing as well as in a laboratory setting. This meant that there could not be a need for a rigid backplate, thus a grasper-style device was used. By using a grasper-style design, the tissue can be compressed between two load cells without the need for an additional surface to test on. The secondary set of design requirements was that the device needed to be as minimally invasive as possible, while still being capable of recording forces within plus or minus 5 millinewtons and overall tissue thickness, which is why we ultimately decided to use two TAL 220B 5-kilogram load cells at the jaws and a quadrature rotary encoder.
The load cells and encoder wires from the grasper are connected to a National Instruments DAC, which then feeds the data to a computer. The computer runs a scissors console application which reads the voltage and encoder data at a fixed sample rate of 1000 Hz and displays a live graph of the data being read. This is useful in case of equipment malfunctions, like a loose wire. At the beginning of each data collection trial, the grasper is stretched open and closed to ensure that the index pulse is triggered on the encoder. This is done so that encoder positions are consistent across trials. The application produces beeps at the beginning of a trial to remind the user to stretch the grasper. The console then produces a series of beeps for the user to grasp with consistent duration and frequency in order to minimize differences caused by potential viscoelastic effects in the grasp tissue. The load cells on the grasper are calibrated by applying known weights before and after testing.
The following video on the next slide presents the grasper device being used to test porcine spleen tissue in an in vivo setting.
One, two, three, four. The force and encoder data produced by the grasper device can be analyzed in a variety of ways. One way we analyze the data is to compute the stiffness of a tissue, which can be observed from the slope of the force displacement curve. After data collection, we calculate the angular position of the jaws from the encoder ticks. Then we obtain the distance between the jaws from the angular position and grasper geometry. We then obtain the displacement of a tissue by calculating the change in distance from the beginning of a grasp, which is initial contact with the tissue. Unfortunately, due to quantization noise from the encoder, it is not feasible to calculate a numerical derivative, so instead we utilize numerical curve-fitting algorithms on the equation shown in the bottom right of the slide. The derivative can then be approximated by computing the derivative of the resulting fitted curve.